Math. There's a lot of math in data science, machine learning, deep learning, and on and on. And all of the concepts that you need to learn don't really have a frame of reference when you're just starting out. So that's what I want to do. I'm not just going to tell you what you need to know. I'm also going to tell you where it fits in your workflow, because at some point you have to create value with it and you have to apply it to your day-to-day work. And it's a whole lot easier to learn this stuff if you can look at it and say, okay, this is what I'm actually going to do with the math, and it's not just some abstract concept with Greek symbols and all this other ugliness. So the basics that I need to cover with you are your algebra. Yeah, you need algebra. You need your just straight up analytical geometry. You need calculus and a lot of calculus. You're going to go through the majority of calculus. Linear algebra, now, getting into more complex information theory, topology, graph theory, understanding the fundamentals of the machine learning models and also of data gathering and experimental design, and not just statistical experimental design. You need a lot of stats, but you also need to understand the scientific principles behind experimental design. Ties into logic. We don't talk about where all this stuff fits. So let me dive right into the workflow, and I'm going to give you a perspective kind of from front to back of where you're going to use each one of these mathematical concepts, and hopefully this frames things a little bit better as you're learning each one of these topics. So first thing first, you have to gather data, right? So when you're gathering data, statistics heavy. You're doing a whole lot of exploring your data and understanding your data, trying to figure out what data's out there. That's a whole lot of just basic descriptive statistics, not a whole lot more to it. You definitely need calculus to understand your basically executing your statistics. You need calculus. Otherwise, a lot of statistics doesn't make any sense. So that's your data gathering. Now, you have data. What are you going to do with it? You have to clean it. You have to transform it in some way. You have to do some feature engineering more times than not with it. And in those cases, again, you're still using a lot of statistics, but you're also getting into more of your differential geometry and topology. You're also using a lot of linear algebra and calculus, multivariate calculus, to understand what that data is composed of. What systems does that data potentially describe? How would you better transform that data to be cleaner and more ready to use, not only in feature engineering, but also to be consumed to train a specific model to learn a function? Now, that's actually a really complicated and dense mathematical section of data science and machine learning. And we're just talking about the data pipeline. We haven't even gotten to the models yet. We're just exploring data, and there's so much math that you use in that whole ball of pulling data in and transforming it and understanding the high dimensional spaces that it lives in. And it helps, the differential geometry and the topology side of this and the graph theory and even the information theory. Now that you've put your data into a format that you can understand, now you have to save it. Now you have to put it someplace, and that's really a high dimensional understanding of data and understanding, the background geometry behind where this lives, and the linear algebra that describes the matrices and the transformations that happen to matrices in order to get them ready to sometimes just be saved in a data structure, and other times to be fed in and served to models for training or for serving inference. So that's your data pipeline, and there's math. Isn't it kind of crazy? Just at the very beginning, we haven't even gotten to the models, and we're still knee deep into the mathematical concepts. Now, when you look at research is actually the next phase that comes after all of this data gathering and pipeline creation. What do you need to understand in research? And this is where logic comes in, and experimental design, not just statistical experimental design, but really the science behind experimental design. And as you start going in this direction, you need to understand causal inference. And again, this comes back to a good understanding of information theory, of the graph math concepts. Those are huge when it comes to understanding causal inference. What's also important to understand is the fundamental process, and this is why I come back to logic, of creating experiments. And then you come back to some of your more basic statistical measures to validate experimental design And then once you have done the experiment, to understand whether or not you've proven anything. Is that causal graph sound? And now you have to analyze counterfactuals. This is an entire other area of math that you do have to get into in order to understand whether you found something that's just basic correlation or whether you have the evidentiary support to say, I found a causal graph. I found causal relationships between my data and a system that I am measuring. I have a higher degree of confidence that the function that my model has learned has causal features in it. And so I have higher confidence in this function actually representing the system under measurement. That's math heavy stuff. And it's more about the math and intentional model selection. And here's where we begin to get into your actual understanding of models, because models as they are, just your basic canned models, don't take a lot of math depth to understand. The functionality, you can read a very simple tutorial on a model architecture and you can understand it very well, but you have to understand concepts like architecture, or excuse me, optimization, to understand more deeply how the architecture works and how you can use different mathematical constructs to customize each one of the models, and how that customization is going to potentially lead to a more accurate model, or a model that takes into account more of the system constraints or the business and operational constraints to build a more valuable model, something that's more effective for that particular business case. So this experimental phase now leads into your model selection and more of your traditional model development. And that piece, kind of the end of your data science workflow and your last piece of your data science lifecycle. And again, linear algebra comes back into play here. Topology heavily comes into play. Graphs, I mean, that's what a model is. Pre-trained, that's an architecture. It's and the deeper your learning algorithm is, then the deeper you have to understand graph math. And again, back to information theory, optimization concepts. Those will all help you understand your model well enough to customize it. You don't just customize the features that you're putting in and do the feature engineering. You're also going to customize the architecture of the model that you use to hopefully learn something interesting about the system under measurement, and then iterate through that process, and typically iterate across a huge number of different types of model architectures and different customizations to specific model architectures. And then the evaluation of models against each other, we're back to statistics. We're back to a lot of your traditional statistical measures that helps you understand not only the experimental outcome, but also to understand when you're comparing models against each other. You can do a lot of automation if you put in the basic statistical measures and automate your selection process. And so there's a lot of automation here. However, you understanding the core concepts that are behind your evaluation of each model against each other and your comparisons of each model's performance against each other, those are very important from a mathematical foundational perspective. And so you have to understand those in order to be an effective data scientist and to create reliable models. Now, reliability, we're at the very end. In the maintenance phase, we have to deploy a model that lives in production, that works for the business or for the particular use case. What is that system that you're measuring? What is that system that you are simulating? What function has the model learned? Now that has to go into production, and you have to monitor it. You have to watch out for drift, because if you don't have the entire causal graph, which you don't really ever, maybe somebody else lives a charmed life. I don't live that life. But now that you have an imperfect model, and remember, imperfect models can still be functional. They can still meet a business need and they can still return value. But they're dangerous because you have to do the math. You have to do the exploration to understand how the model works. And that's a core concept of reliability. And there is, I mean, just throw every piece of math that I've explained to you before, and those all come into dissecting a model to understand what it's actually learned, and to, again, support where those high-dimensional data spaces, where we have a high level of confidence in the inference, and those spaces where either we didn't have enough data to make any sort of significant discovery or any sort of significant finding. And so anytime we have inputs that fall into that space, or anytime that we have an intervention, something that happens in the system, anytime we are living in those spaces in our data where we simply don't have confidence in our understanding of how interventions affect the system, those are the areas that we need to have some sort of augmentation or large warnings that say we have unpredictable model performance that'll occur in these different scenarios. Once those are published, you can actually push those models to production. They can provide value, but your understanding of how the model works and all of the math, like I said, it's just everything that I've mentioned before. All of your understanding of math comes into play. You use that to create that explainability and that understanding of where your gaps are. And then you use that in production to create these safety nets that prevent your model from doing horrible, horrible things in the real world. And then you monitor it and you say, okay, we were very confident in these areas. Now, how's it actually working? And again, you're back to basic statistics here and your normal monitoring metrics to see, something's going wrong in production. You're also back full circle, checking out your model inputs and watching your inputs for any sort of change. And again, this is basic statistics that will help you understand how your data may be changing and how the quality of your data may be changing, or how your distributions may be drifting. And that will help you maintain your model and prevent it from some cascading failure or doing horrible things in production that you don't want it to do. And the more accurate the function that you've learned, the more accurately that model actually simulates that system and understands the impacts of intervention, going back beyond correlation and towards causal graphs, the more predictably it'll perform in production, the less monitoring and maintenance and continuous retraining that you'll have to do in order to support it. Again, back to all of those mathematical concepts. So that's where it all fits. That's where all of these conceptual pieces fit in your workflow. And what you'll find is that once you've gone through, like I said, your algebra, your analytical geometry, your linear algebra, all of your calculus, a very, very deep calculus, you get into your topology, you get into descriptive statistics, and then more complex statistical concepts. All of those go from, here are these high-level categories of mathematics like information theory, graph theory. Now you start going into implementations. And that's what I've explained a bit to you, is if you look at the workflow, you'll be able to not only learn those high-level concepts, but also look at specific implementations like exploratory data analysis or optimization and say, oh, okay, that's important for me to focus on because it is a key piece of my workflow, and that's something that I'm going to be doing over and over and over again. When you focus on things like counterfactuals, those are huge. And so now you know what to listen for because you have a framework. You can attach it to different pieces of your workflow, and that's how I want you to learn math. Yes, definitely learn the high-level concepts, but as quickly as possible, relate what you're learning to what you'll actually be doing in data science, in your workflow, in your day-to-day. How do you produce value? Connect your math as quickly as possible to that workflow, and you will have a point of reference that makes learning math so much easier. And you'll avoid going down rabbit holes that, while some of them are important from a conceptual standpoint to understand, the deeper down that rabbit hole you go, the more time you can end up wasting learning something that, not that important when it comes to applied data science and machine learning. So I hope this has helped.